everyone, Quantama here. Today we're going to be taking a dive at the next logic behind video, this time being about vectors, specifically two-dimensional vectors. If you can understand the basics and the logics behind everything in two-dimensional vectors, future topics like 3D vectors and tensors, starting off them becomes a bit more easier as you know the logic behind the two-dimensional vectors. One thing to keep in mind is that we map down vectors from real life onto a plane/paper. Like vectors in reality don't exist as arrows and straight lines. Now let's make a line. Right now all this line has to itself is its length or magnitude. But now let's add an arrow to it. Now it's a vector. Now it has a magnitude and a trajectory of where it is going towards. By looking at it, we are making 5 different observations. First and second being from before that it has a length, also called magnitude, and that it has a trajectory. Trajectory like direction you can say. But there's a different thing behind the word direction in vectors. So for now I'm going to call it trajectory. The third observation being the point over here from where the arrow is coming from is the vector's starting point, which can be any capital letter you want. A capital or B capital letter, C, whatever you want. Fourth observation being that the point over here to where the arrow is going to is the vector's endpoint or called the terminal point, whatever you want to call it, which can also be represented by any capital letter you want. B capital letter, C, P, Q, Z, whatever you want. The fifth and last observation is one that is not exposed to the eye but is hidden. Let me draw it so you can see now. The angle of the vector with the horizontal, with the x-axis, also called the vector's direction. Yes, this angle with the horizontal of a vector is known as its direction. These were the all 5 observations we were able to make about a vector. But this vector that I've made is just on a paper, nothing more than that. Now I am going to map it onto a coordinate plane. Now it has much more observations to it. We can find out even more information regarding it. One thing is that we can map the vector wherever we want on the coordinate plane only if its magnitude and direction is correct. Then there is no problem. But we intentionally move the vector, if it is placed somewhere else on the coordinate plane, to the origin of the plane. The starting point of the vector to the origin of the plane. We do this so we can have the ease of calculations. A vector with its tail on the origin is known as a position vector. But even though we will move from somewhere else to the origin of the coordinate plane, its direction and magnitude should remain the same. You may ask, how do we move a vector somewhere random on the coordinate plane to the origin of the coordinate plane through calculations? Well, we do that by finding the change in x and change in y between the starting point and the terminal point of the vector. After we find both the change in y and change in x and move the vector to the origin of the coordinate plane, the vector's starting point is obviously going to be 0, 0 as it is on the origin, but its terminal point is going to be the change in y and change in x itself. And this is obviously because we are moving from 0, 0. And now that this vector is here, we can make a new and 6th observation, the forming of a horizontal and vertical vector by the vector itself. A bit confusing, but just see. The horizontal vector tells us how ahead the vector has moved, while the vertical vector tells us how above the vector has moved. Just like I said, we can move vectors wherever we want on the coordinate plane. I am going to move this vertical vector from here to here for ease. What ease, you'll see later. I've done all of this, but now I'm thinking, how do I represent a vector? How do I represent its change in x and change in y? Well, I can't use the Cartesian coordinate form because the Cartesian coordinate form tells us x, y of a point, while a vector is a whole line which has a change in x and change in y. I need a new form. That's why I am going to choose matrices. Matrices have a wide variety of uses, and that's why I am going to use matrices for vectors. I'll make the first row the units of how ahead a vector has moved and the second row of how above a vector has moved. Basically, the first row will be the change in x, the second row will be the change in y. As this matrix contains information regarding a vector in a column, I'll call this a column vector. Back to the vector, as this horizontal vector obviously can't move above because it is horizontal and is moving along the x-axis, its column vector would be x and 0. And as this vertical vector obviously can't move left or right and can only move above and is moving along the y-axis, its column vector would be 0, y. Since the horizontal vector and vertical vectors are connected to each other at the horizontal's head and the vertical's tail, and if I connect the horizontal's tail, which is the origin, and the vertical's head, which is the vector's terminal point, wouldn't it just mean that I would be adding the horizontal and vertical vectors to get the original vector itself? X, y. So basically, the vertical vector and horizontal vectors, when added together, represent the column vector of the original vector itself. Oh my god, what is this? I have just killed 2 birds with 1 stone. That's correct. This is not only from where we now know why we write the x component and y component in a column vector like that, but also now we know how we thought of the head to tail rule. Head to tail. Go through the horizontal vector, then the vertical vector. Add them both, head to tail. Oh my god! I have found yet another thing once again. Whenever vector addition happens, whether it be about 2 separate vectors or about the vertical vector and horizontal vector of a single vector, we always form a triangle, which means we can implement rules regarding triangles such as Pythagorean theorem and trigonometry. Remember when I said this is the length/magnitude of a vector? Well, I was incorrect. Length and magnitude are actually 2 separate things. Magnitude is the quantity the vector holds, whereas the length is the literal length of the mapped vector. Let me make it easy. If I were to draw a vector of force of 100,000 Newton, now would I really draw a vector that is 100,000 units long on the coordinate plane? Yes.
Why don't you shut your mouth up?
No. That is a waste of time. We would map the vector down by mapping the whole coordinate plane down. By, for example, saying that 1 unit equals to 10,000 Newton. Now, when we make the vector, its length would be 10 units, whereas magnitude would be 100,000 units. That is the difference. And as the whole coordinate plane would be mapped down to, we can calculate the magnitude through a calculation. Back to the original vector. Now, as this is a right angled triangle and these are 2 sides of it, perpendicular and base, and we want the magnitude of the main vector itself, can't we just apply Pythagorean theorem? Hypotenuse square equals to perpendicular square plus base square. Hypotenuse is magnitude, perpendicular is x component, base is y component. Taking under root on both sides, magnitude equals to under root x square plus y square. X component square plus y component square whole under root. There we go. That is the formula for a vector's magnitude in terms of its components. Another thing, better than writing the whole word magnitude, we use the vector's identity itself, the vector's name. How do we know its name? Well, one point is O, the origin, and let's say the terminal point is A. Then the vector is OA with a small line with an arrow in it. We could also say this vector is lowercase bold a with a line with an arrow above it. These are the ways we can give a name to a vector. Back to the formula. We also put 2 borders beside the vector's name just to show that this is a magnitude. Just give it an identity. Give the magnitude an identity itself. Now let's move on to the direction. As we need to know the angle with the horizontal or the positive x-axis, and as this is a right angled triangle, we can just apply the trigonometric tangent function, which gives us tan theta equals to y component over x component, theta equals to tan inverse or arc tan y component over x component. There you go, simple as that. We have yet another new formula for the direction or the angle with the horizontal or the positive x-axis. And we are done with everything related to a singular two-dimensional vector. We have studied all of its ins and outs. Done. But now, what if we had two vectors? That's where the real deal comes in. To find their resultant vector, we obviously add them through the head-to-tail rule that I told you a bit before. We just move one vector, put its tail with the other's head, and then join the other's tail with the first one's head, which would be the resultant vector, and then add the both vectors together. Now that we have their head-to-tail diagram, how do we add them to get the resultant vector? Through calculations. How do we do that? Just add their respective x components with each other to get the resultant x component, and then their respective y components with each other to get the resultant y component. Okay, that's done. Vector addition between two vectors. But how do we find the angle between two vectors? Before that, how do we identify if the angle between two vectors is acute, 90 degree or obtuse? Well, both of these queries are solved by the same formulaic explanation. These are two different vectors. Let's call one P and the other one Q. We want to find the angle between them. For an angle, we obviously need a triangle. For that, we find the resultant vector between these two vectors, which would be the third side of the triangle. Now that we have all three sides and we want to find one angle, we will apply the cosine rule. Here is the whole working from start to end. You can pause the video to read it as I'll be moving on. So here at the end we get this cosine theta, product of the magnitudes, and this. What is this? This is known as the dot product of two vectors. Cos theta equals to dot product divided by magnitude product. Now if I reassemble this equation to make dot product the subject, we would get dot product equals to magnitude product into cosine theta. We make an observation here. If we put any angle between 0 or 90, the answer would always be positive, which would mean that the angle between two vectors is acute. If we put any angle between 90 and 180, the answer would always be negative, which would mean the angle between two vectors, the two vectors that we're talking about, is obtuse. But if we put 90 in cosine theta, it would get multiplied by magnitude and it would be a complete zero. Which means whenever two vectors are perpendicular to each other, the dot product will always be equals to 0. So simply, the dot product basically tells us the type of angle between two vectors. If it's acute, obtuse or perpendicular. How do we find the value of a dot product? Well, this is basically what a dot product is. Okay, back to the basic formula. By sending cosine to the other side, we get theta equals to cos inverse or arc cos dot product divided by magnitude product. And that is how we find theta, basically the angle between two vectors. We just put the values of the magnitudes, their dot products, and then apply them with cos inverse to get the angle between two vectors. Next, we move to vector enlargement or de-enlargement. This happens when a vector is multiplied by a scalar. The scalar scales the vector by enlarging it or de-enlarging it. If the scalar is greater than 1 and is positive, it is enlarging the vector in its original direction since it has a multiplying value and it isn't changing the component's signs. If it was negative, then it would have sent the vector in the opposite direction, enlarging the vector as it would have reversed the component's signs. If the scalar is less than 1 and is positive, it is de-enlarging the vector in its original direction since it has a dividing value and isn't changing the component's signs. Same for this, if the scalar was negative, it would de-enlarge the vector and send it in the opposite direction. The vector was multiplied by a scalar of 1. Obviously, it would remain the same size and the same direction. But if it was multiplied by negative 1, the size of it would remain the same, but its direction would become reversed. The last topic that we have now regarding two-dimensional vectors logic behind video is regarding the unit vectors. As the name contains the word unit, which kinda means 1. The unit vector has a magnitude of 1, which means if we put their x and y components in the magnitude formula, the answer will always be equal to 1. By the way to identify a unit vector is that they have a cap over them, a arrowhead cap. How do we find a position vector's unit vector? Basically, how do we find a unit vector in the same direction as the position vector? All we do is divide the column vector of the position vector by its magnitude. Basically, we divide the x and y components of the position vector by the vector's magnitude to find the x and y components of the unit vector. Why do we do that? Well, here's once again the whole derivation of how we do that. You can pause the video to once again read it. Now lastly, there are two special unit vectors that I want to discuss. The I unit vector and the J unit vector. Well, the I unit vector is a vector that goes along the x-axis and has a magnitude of 1, hence having an x component of 1 and y component of 0. And the J unit vector is a vector that goes along the y-axis and has a magnitude of 1, hence having an x component of 0 but a y component of 1. And because of them being like this, we can use them to write the vectors in another equationic form, the unit vector form. How do we do that? Well, let's take this vector. It has an x component of 4 and y component of 3. Basically, its x component comprises of 4 separate I unit vectors and y component comprises of 3 separate j unit vectors. And so we can write the x component of this vector as 4i, which means it has an x component of 4, and the y component as 3j, which means it has an y component of 4. 4i plus 3j. And see, we can go back to the column vector form from this by expanding the I and j unit vectors. I really hope you understood all the logics behind how we have all these formulas and workings in the topic of vectors, more specifically two-dimensional vectors. I mean, you can use all the logics behind this to find out the logics behind three-dimensional vectors too. But I am going to help you in that in a later video. Not soon, but a bit later. Who knows when, we'll see. If any of your friends are having difficulty in understanding this chapter, please do share this video to them. It would really help them out. I hope it does. Lastly, a mandatory thing to say I guess, please like the video and subscribe to my channel. These videos really do take a whole lot of effort than you might think. For me at least. Goodbye and Assalamu alaikum. Appreciate you watching.